Hello, this video is for Dr. Regentova, and the purpose of it is to demonstrate our CPE 300 final project, which was a microprocessor. Okay. So, before I actually show you how it works on the D2 board, I would like to go over all the components that are in the design file. So first, we have the clocking logic. The inputs are clock, start, reset, stop, continue, pause. All of those signals are controlled by the D2 board except for the pause signal. The pause signal is actually asserted from the control unit over here. But going back to the clocking logic, all it does is simply from the start it just increases the state, or increases the state, and each state that corresponds to it produces a 3-bit output signal which controls the control unit. So first it starts at state A, which corresponds to 0, 0, 0, and then next it goes to state B if the start button is high, and then it goes to state C, D, E, F, G, just automatically if it's in those states. Then finally, once it gets to state H, it just goes back to B. Okay? So once those states are received, those values go into the control unit. Based on those values, it will produce assert signals to all of these outputs. And all these outputs connect to all the components that are inside of the microprocessor. As you can see, it's very repetitive, but very important, obviously. And it just goes on down to like 1,000 lines. It's too much. Anyway, let's see. Here we have a multiplexer, and let me see if I can zoom in. I can't. Okay, I'll just go closer. Okay, and it has 3 inputs, and when the select is equal to 0, 0, then it just takes it straight from the ALU. If it's 0, 1, then it gets from the standard input. When it's 2 or 1, 0, it just takes it from the RAM. Okay, from there it goes in the register file, and based on the address that's provided to the register file in A or B, it will write to it, it could read from it, it could do, well, that's about it actually. And once it leaves the register file, it goes onto 2 buses. The higher bus, the top bus up here, is the A bus, and the bottom bus over here is the B bus. It continues down to the buses, goes into the ALU, and as you can see we have 2 buses here, so we're not just using a 1-bus design, but we're not technically using a 3-bus design because we have a lot of port-to-port connections, so since a lot of things aren't just like being on the same port, you can't really call it 3-bus design, so I'm going to call it like a 2.5. So since we're doing that, we were able to make a more greedy approach for our ALU. I know combinational logic would have been like the most efficient, but for the simplicity of the design, we chose to go with a one-hot state assignment. So basically what we did was we concatenated all of the input signals, and since no 2 ALU signals would be asserted at once, then by using one-hot state assignment we made it simpler, and that's about it. So like basically when the string is equal to 1, 0, 0, 0, 0, all that jazz, we add, and then when the next bit is 1, then you subtract, next bit is 1, you do not, and then increment. And also I included a decrement, even though the assignment didn't call for it, but that's just like a common thing that I think processors need, even though we don't use it. Okay, so after that, it goes into this register. It's titled AC, but all I did was just copy it from my accumulator register that's up here. But it doesn't really serve that purpose. Some of the inputs are actually grounded. But all it is just a 8-bit register that holds the value, that loads the value from the ALU, and automatically it will just spit it out to the conditional logic, and the conditional logic, based on the previous arithmetic operation, will provide signals that tells you whether it was greater than 0, less than 0, 0, non-zero. I think that's it actually. Okay, so now let's go up and let's actually look at the accumulator. The accumulator has a clock input. It can load, it says load address, but that's just data. Read, and reads to PC. So the reason why it reads to the program counter is because we were having like some really difficult timing issues, and we needed to be able to hold on to the program counter for a longer amount of time than the signal than we were able to use just by connecting the program counter to the ALU. For some reason this worked. I honestly still don't know exactly why, but this is what works. I'm sure that we could get rid of the accumulator, but for now it stays in. And that's really all it does, is it just holds on to the address of the program counter. That's all it does for the most part. Here is the memory address register. Our design originally had a memory address register and a memory data register. The memory address register would just hold the address, the memory data register would hold the data. But since we really didn't need to store any data, we were able to actually figure out solutions like that would allow us to write straight from a port instead of going through a register to decode it and whatnot. The only inputs on here are the input from the program counter, also an input from the ALU, clock, a read assert, load assert, clear, and a select. So you can choose either to load from the ALU or you can load from the program counter. Give me 1 second, I need to charge my phone. Oh, this is not going to work out. Give me 1 second. Alright, there we go, that's a little better. Alright, despite me being a computer engineering major, I do not care too much about having the fastest phone or the phone with the most storage capacity, so I had to like upload the video to my computer and delete it. So I might have to do that one more time, but hopefully not. So the imports, not imports, the inputs to the instruction register are the clock, reset, load instruction register, read from the A port, read from the B port, which is right here, and the data that comes in is just straight from the RAM. So the outputs are actually identical. They both contain the least significant bits, the 8 least significant bits. So with our design, or what the assignment called for, was to have like the memory address or the constants just in the least 8 most significant bits. So the difference between the two ports are just the output connections. So this one connects to the ALU or the A bus, and this one just goes straight to the RAM, which is right here. And the advantage to that is when we're writing to the RAM, once the instruction is already loaded into the instruction register, we're able to just write to that address immediately because we already have it latched in the instruction register. So that saves like a clock cycle. Other than that, there's not too much more. Right here is a register, and all the register contains is whatever is on the A bus when we need to output to the LEDs. So just really simple, just an assert signal for STD out, reset, clock, and also the data, which comes from the A bus. And these two bad boys over here, these are just 8-bit numbers, or 8-bit signals to the LED outputs. This one is for the STD out, so you can display up to 3 digits, and this one is for the SDN, and it displays only 2 digits because I thought it was sufficient for us to only have to display the numbers 0 through 99 in case you want to input via SDN. And right here is just the logic for the SDN. So all it is a counter that is connected to an adder, basically. The output of the counter is connected to this adder right here. And if you press this button right here, it increments it by 1, but if you press this button right here, it will increment it by 10. And the signal is just connected to this OR gate, which is also ORed with the increment once signal, and that drives the clock. So nothing too fancy, just a quick solution. So now that that is done, I think we are ready to demonstrate. So first let me compile it real quick. Okay, and the way I'm going to do this is I'm going to have 3 different MIF files to show you 3 different processes that the microprocessor can do. Hopefully that's sufficient to show you that this thing works. Okay, so the first one is titled branch greater than test. So basically all it will do is add 2 times n to the add 2 n to the minus 1 times. So first, here's the assembly code. It will load 1 into R0, load 2 into R1, 0 to R2, 26 into R3, add R2 to R1, subtract R3 to R0, and then it will display whatever the contents are in R2, and then here just the values that correspond to the MIF file. So it's already compiled, and let's see, let me go over here. Oops, not that. Okay, and that's the correct file, so now I am going to program it as soon as I can find the programmer. And it programs. So here it is, and as you can see, oh no, it doesn't work. And that's because the start signal isn't asserted, so let's assert it real quick. And then let's reset it. And it's this button right here. Can't really see, the lighting's bad. And as you can see, it just basically multiplies. Multiplies 2 times n to the whatever R3 was, which was 26. So multiplies 2 by 25. And here I'll show you it doing it by 3, or multiply 3 25 times. So let me just change this to 1. And these compile times just take forever sometimes. Not so bad on my computer, but in the lab it takes forever. Alright, so let me just program it. I did program. Okay, and as you can see, since the start is asserted, then it's 75. So that is branch greater than. Okay, so I have another file for branch less than. And go right here, just change this to 1. And compile it. Okay, so while that's compiling, I'll go over through the algorithm. So first I'm just going to load 3 into R0, I'm going to load 1 into R1, then I'm going to, sorry for the poor handwriting, but I'm going to subtract R1 from R0, since 1 is less than 3, then in theory it should branch less than, and it's going to branch to address 36 right there. And then after that it's going to load from the address 36. The instruction is it's going to load 5 into register 2, and then it's going to output. Here are the binary that corresponds to the MIF file, and it's done, so let's program it. And it programs, okay, and it didn't work because sometimes it just doesn't work on the first time. You just gotta clear it a few times. No, oh, there it is. 5. And the reason why it doesn't work, like, all the time is because this thing is clocked at 50 megahertz, meaning it does 50 million clock cycles per second, and sometimes when you're pressing the button it just doesn't latch properly. So I have one more, and let me just get this set up. Just change this to 2. I'm also going to send you these files if you want to play with it yourself, if you have the time, of course. Compile it, and then while it's compiling I'll do the same thing and go over the algorithm. So this one is for testing read and write. So what I'm going to do is I'm going to load 5 into register 0, 10 into register 1, and then I'm going to write the contents of register 0 to address 64, and then I'm going to read the contents of 64 into register 1, then I'm going to output whatever's in R1. I'm actually going to change that from 5 to something else after I run it. But yeah, it just compiled, so yeah, as you can see, it doesn't really work off the bat, so when you clear it a few times, you get 5. And let me go back to the RAM file. Yeah, this thing has a lot of files. Let's see, I think I passed it. And where it loads 5, I'm going to load, what do you think, 10? And compile it. Alright, it's done, so let me run it. Now we're on the board, and like usual, it doesn't work right at the bat, so you gotta clear it a few times. And there it is, 10. Okay, but that's about it. Hopefully by showing you these things, you would believe that the branch instruction works. What else? The and, or not, those are really simple. And yeah, oh, one problem though. Like I said though, since this thing clocks at, it runs 50 million clock cycles per second, I was trying to do load immediate, or I'm sorry, STDN, and then display it on the D2 board. By the way, this is the STDN, these buttons right here. So this one updates to 1, this updates 10. Okay, well, what I was trying to do was I was trying to load whatever's on STDN and then immediately display it out to STDO. But in order to do that, you have to have pause signals, and then like this button right over here is the continue button. So like I would load it in properly and whatnot and then press continue, but like I said, this thing clocks so fast, the continue button actually gets asserted more times than I want it to. It gets asserted more than one time, so basically it just doesn't display it properly. Not all the time. Sometimes it does, but not all the time. But what I will do is I will send you a simulation of the STDN. And if you want to see a simulation file in this video, I'll show you one. So I guess this one was for the previous algorithm. And let's let's go all the way back to the beginning. Yeah, these things are just because it's a timing simulations, and they have some artifacts that are in the registers that get loaded up, so that's why the timing has to be exact. So here, you can just look at it through the opcodes. Opcode is right here. So 14 corresponds to load, it just loads everything. 12 is the write, and then 13 is read. So then afterwards, it goes to 1. And 1 is for STD out, so in order to see the contents, you just go down here, all the way down wherever STD out was, right here. And it shows 0, 1, 0, 1, or if you read it the other way, it's 1, 0, 1, 0, and that is 10, which corresponds to the value that we inputted in. And also, I'll show you the RAM file as well. Is this RAM 2? Okay, but yeah. So here is where we actually load up 10, and then on, what was it, 64? Let's see, 64. Oh, 64 is where we stored the value, and then yeah, it just gets the value from here. But as you can see, nothing's stored here in 64 yet. It totally gets done all by the microprocessor. That's about it. Last words. Thank you for a good class. Learned a lot. Hopefully this demonstration shows that I did. I feel like if I had to, I can make a 1 bus or a 3 bus design or 2 bus design pretty easy. But yeah, you're a great teacher. Thanks a lot, Dr. Regentova, and I will see you next semester.